you need to sit there. I just shoved them there.
Stay in the back.
Oh, okay. Like the back. That's terrifying.
So I should not point at you now. Yeah. I think he will be good.
See ya.
So you wanted to...
I will do this. Yes, it's
Good.
fine with that.
Better.
Better, yeah. Good morning, everybody. Welcome. Goedemorgen allemaal. To this momentous event, I would say. I promised that I would not make any jokes, but I will do that later.
I have to be close to you because there's only one microphone.
Okay, yeah, thanks. I don't know the good morning in Japan, but anyway. So yeah, today we have the last activity of Momo as a student. A series of 3 things are going to happen today. So first we have the public presentation of about half an hour. And we do invite you after this presentation, of course, to ask questions, to warm her up for what the students call the dreaded engineering exam, which, if you have gone through it, and the students who have done that, the former students who have done that can confirm, it is just a jolly meeting where we have a nice discussion for about an hour. So after that, we will release Momo. She can come back here, where the committee will debate about the grades. We have a set of rubrics for that, so we will make sure that everything is in order. And then after about 20-25 minutes, we ask you to come back in, communicate the grade, give you the feedback, and then we will come back here in this room for the final part, which is the diploma ceremony, where you will have the diploma. Now, since we have a new Pope with white smoke, I no doubt that we will have white smoke for you as well for the diploma. Although I must say, the flowers here are premature and they were blocking our way, but so only thing left for me to do is now to introduce the committee. Our esteemed colleague, Dr. Angelo Cervone, he preferred to stay at the back because he is shy and I was not supposed to point at him, but he's at the back. Angelo, thank you very much for joining us. And of course, our external examiner, Dr. Alessandra Menicucci. Also, thank you. She's from our sister section of Space Systems Engineering. So that's all I have to say. I'm not going to try to explain this title. You know better than I do. So the floor is yours.
Thank you. Okay. So first of all, good morning, and thank you for everyone being here today. It's really nice to see so many faces. And I'm here to basically tell you a bit about my thesis, which has the title of A Contribution to a CubeSat ADCS Testbed for Educational Purposes. Now, this is a mouthful, and it probably doesn't make any sense right now, but I hope that over the next 30 minutes, you'll get a bit more of a glimpse of what I've been up to for the past few months, close to a year. So just to begin, I want to just go over the agenda and what I'll be talking about. So I'll give a 5-minute introduction on the topic, the reasons why I chose to do this. Then I'll go on to the research objectives, so what exactly I did. And then I'll go through the functional simulator, how that was built, and then the real-time simulator itself. Finally, I'll conclude with some I'll finish with some conclusions and recommendations. So first, a bit of an introduction. An introduction to CubeSats. CubeSat is a cube satellite. It's a 10 by 10 by 10 satellite that was first developed in 1999 as a fast and cheap alternative to developing educational purpose, things like this in space. These are 3 examples that I pulled from my research. First is a 3-unit, so a 30 by 10 by 10 satellite. It's a research satellite from Kenya Space Agency. We also have the Delphi C3, which is a 3-unit research satellite. And then we also have a 1-unit satellite from University of Munich as well. What I wanted to highlight here is the exponential growth of CubeSats being used for research purposes. As they're really cheap and they have a really fast turnover rate, you can see people are just using them for more research. One of the things I wanted to look at here was the yellow, orange, and light blue. And these are university, schools, and institutes. And this is the area that I'll be looking at for testing. So as you can see, this area has continuously grown throughout the years, even since the beginning. And even in the most recent years as well. But as we have cheaper, as it's cheap and it's fast turnover, we also are using cheaper components, which means that the survival rate also gets impacted. Some statistics that I found during my Listra study, 21% of a study of 178 CUBE satellites were dead on arrival. That means that they were put into orbit, but they didn't even start. You also had 40% of those which stopped after the first year of operations. And this is a huge percentage of these satellites which are not working. So I looked into, okay, who was building these satellites? Why were they failing? So what I found was that university-led or education-led missions were only 60% successful, while agency-led, larger budgets, larger resources were around 80% successful. So then I started looking into subsystems. What was the cause of all of these issues? Why were they breaking? And these were the top 3 that I found. So first is the electrical power systems, turning the satellite on. Then you have communications, communicating to your ground station. And then I also had the attitude, determination, and control system, which is what this thesis was focused on. I decided to pick this specific subsystem, one, because of the resources that were around me. Firstly, my supervisor had knowledge on ADCS, so it was easier to get help with. And also, I was able to look at testing with hardware and with just software. So then I asked the question, what can I do to help improve the rate of these educational satellites? And one paper that I found, which was looking at how to improve reliability, was number 7, testing, testing, testing. So then I looked into what kind of testing facilities, how are CubeSats tested, and one of them was doing real-time testing. So you can have a variety of different test methods. System. You're testing one specific subsystem, maybe you're testing a specific component. But I wanted to look at the last stage, which was integration of a system. So then I looked into, okay, something called real-time testing. This is basically when you run it, where you're able to see latency errors. And this was something that I thought was a bit out of scope for educational-based projects. Majority of the setups I found were over 10,000 euros, which is very unachievable for a student like myself. So now I want to introduce some terms that I'll be using throughout this presentation. The first one you heard me mention already, which is real-time testing, and then also the opposite, which is non-real-time testing. So when you run a simulation and you have variable step sizes, those step sizes mean there's a variation in the time intervals that are used. So you get a simulation, but it's not necessarily including those latency issues. The two other things, within real-time testing, you have software-in-the-loop testing, which is just using your software, your computer system, seeing what issues would have with a simulated environment. And then you have hardware-in-the-loop testing, which is then you're incorporating pieces of flight hardware. So this could be a sensor, this could be a camera, a payload, things like this. Now I've gone over the general background of my thesis. So I decided to pick an education CubeSat mission as my general purpose. I wanted to look at testing, and I chose to look at real-time testing with ADCS components. So here I came up with my research question, which was, to what extent can low-cost hardware and simulation tools support real-time testing of CubeSat ADCS algorithms in an educational context? Now, this is a lot to go over, but basically what I'm trying to say here is that I'm looking at low-cost hardware and how can I create a real-time testing environment. So I separated this into 4 sub-questions. The first one looks at how do you build it? What do you need to build a simulation to test ADCS? The second is, okay, then if we start doing real-time testing, what are the limitations and the benefits of that? Then I look at, okay, is it possible to include hardware in the loop testing? The main focus will look at software in the loop testing for this thesis, but I wanted to see, is it even possible to include hardware? And then lastly, for the people that I'm building it for within education, is it made for an educational purpose? Is it available to meet the needs of student-led missions? And to do that, through my Listra study, I looked at different tools, different softwares that I could use to create this test environment. So I landed on using MATLAB Simulink. I'm sure all my other people who studied here know what MATLAB and Simulink is. This was under an educational license, so this was something that I could use for free, not necessarily the university, but as a student, if I was in a student team, this would be something that was accessible to me. MATLAB and Simulink is a modeling tool, so you can create those simulations within it. Then for my real-time environment, I decided to use a software called Eurosim. Now, Eurosim was something developed a while ago, but it has a rich heritage of being used for different types of real-time testing in missions. For example, the Gaia mission was used this software for some testing. And lastly, when I build my simulation, there are many components inside of it. And I can't, well, if for the entirety of this thesis, I could have made every single component, but what was very useful was to use a library of components that already existed and were used for this sort of testing. So this library that I decided to use was called the GRADS library, the Generic Rendezvous and Docking Simulator, which had sensors, environment models, which were already verified that I could use with minimal testing to integrate it into my simulator. So now I've gone over what tools I'm going to be using. The next part is, okay, now we're going to build it. So first, in this functional simulator area, I'm going to go over the reference mission. So I needed to create a mission to build the simulator around, and then I will build that inside of MATLAB Simulink using the GRADS library. So first, when I was looking at different types of missions, I looked at databases of different types of CubeSats that were being launched, that were being developed, that were being created. And through that, I found that 40% were using 3-unit CubeSats. So that's the 30 by 10 by 10. This was a very popular configuration. We also had the majority of their orbits being between 400 kilometers and 600 kilometers, and usually with a sun synchronous orbit, so SSO, or a low Earth orbit, LEO. So the sun synchronous orbit is you're orbiting with the sun, low Earth orbit, you're in a low Earth orbit. On top of this, I also found that they always, or most of the missions that I looked into, used two primary control modes. The first was magnetic detumbling. This is when you first get launched into your orbit, and you've got to stabilize yourself, and using magnetorquers and magnetometers. And the second was some sort of Earth pointing or sun pointing. So this could be you're pointing to the sun, your solar panels pointing to the sun so that you get energy, or it could be maybe you're pointing a payload towards the Earth. So with this research, I came up with this mission. So I chose a 500-kilometer low Earth orbit. I decided not to include payloads because I was testing specifically the attitude determination control system. So then I used a 3-unit CubeSat and roughly 5 kilograms. And this is roughly the weight of my cat, if you've ever held him. And then mission objective, I made it Earth observation, and then sensors and actuators were picked based on my control modes, which I just discussed. So now I need to create my simulator. So I will be going back to this roadmap every single time to show you how it slowly comes together. But this is first built within MATLAB Simulink, and then it will go to Eurosim. So first we'll build it in Simulink. So first we'll start with the environment model. Now, as I was doing it in a low Earth orbit, I had to think about what environmental perturbations, disturbances would be felt by the satellite at that altitude. So the 4 main categories I included was the gravitational field, the magnetic field, the aerodynamic drag, and the solar radiation pressure. Luckily, these models were already included inside the GRADS file, so I picked these. So these are the ones that I included. As I said before, these were already verified, but I did do my own small unit tests and acceptance tests to make sure that they were corresponding correctly. As you'll see, a lot of blocks will build on a lot of blocks, and you'll end up with something that's huge. So it was really important for me to slowly do small integration tests as I went along. This is what the simulator looked like inside of Eurosim, if you were curious. As I said, those 4 blocks then turn into a lot of blocks, so it's very important to be testing along the way. So this is now my environment model. As you can see, my 4 perturbations. Next is my flight dynamics equations. Basically here I wanted to start thinking about, okay, how am I going to represent the movement of my satellite? How is it going to move around space? Or how can I represent that in terms of equations motion? There's a lot of different ways to represent the movement. And I specifically looked at these 2 main ones, which were the quaternions and the Euler angles. Now, usually Euler angles are used as they are more visually understandable. As you can see on the top figure over there, the 4 angles are the rotations around the different axes, whereas quaternions are a little bit harder to visually understand, so debugging became a little bit more complicated when using them. So, however, if you wanted to use Euler angles, you could. it just means that at certain, so the limitations of Euler angles is that when two angles come together, they have an issue called a gimbal lock, which means that you lose rotation around one of your axes. And this can be a problem, let's say that I'm running my simulation and then a gimbal lock happens, all my results will be thrown off. You can prevent this by adding a small catch, which means that you're changing the way that the different angles are being calculated. However, to remove this difficulty, I use quaternions, which are another way of representing this movement. I also, as my simulation incorporated many different components from many different areas, I had to also think about what reference frame was being used continuously throughout building this simulation. Now, these are the equations that I used for the motion of my satellite. So the first one represents the rotational dynamics, and the second one represents the attitude kinematics. And these were used to propagate and to find the next position. So these components were also included inside my grads library, as you can see here, and these were the ones chosen. So that's my flight dynamics equations, and next is my sensor models. So the sensors that I decided to use were 6 sun sensors, so 1 sensor per surface area, 1 gyroscope and a magnetometer. These components, the sun sensor and the gyroscope were available, however, there wasn't a magnetometer. So I created one myself where I adapted the gyroscope to accept magnetic field values. But it looks like this. Basically what happens is that I created them all to include the different types of errors and noises. This was one of the unit tests that I did here for the sun sensors. As there were 6 different components, I had to really check to see that each sensor was being activated when the sun was hitting that sensor. So this is a really exaggerated view of what the satellite would be experiencing. If this was in real life, it would be detrimental. But just for the sake of this testing, we have included some extreme movements. Another thing that I considered here was adding error models. So each different type of sensor and actuator have different types of discrepancies, errors, which are introduced based on different factors. And that was something that I included and I accounted for. So the way that I gave these values is the different missions that I did during my literature study. I found the components that were being used and used those data sheets to find an average value for the different types of errors. So here's an example of the gyroscope with and without the errors. So that was my sensor models. The next part is my Kalman filter. Now, a Kalman filter is a navigation filter. It takes the noisy data and it gives you your states. In my case, it was just my quaternions. This was because my gyroscope gave me my angular velocity, and I used, my angular velocity. The other 2 values, as you saw previously, the sun sensors were not always active, which means that there were areas of time where there weren't values coming out, which means that I weren't able to estimate those particular points at that period of time. So what I did was I connected both the sun sensor measurements and the magnetic field measurements so that there was continuously some sort of prediction going on. So the way that it predicted it, here's the relation between so NY and NZ are the outputs of my sun sensor. This is how it's related to the field of view and then the azimuth angles. And then you also have how that's related to your sun vector. So the sun vector was something that was simulated, but also internally in my Kalman filter, this was estimated. So I compared those 2 values. Now, this is the output of my Kalman filter. It looks really chaotic, but this is kind of what we wanted. Basically, if you look at the figure on your right, you'll see the different errors. And the 2 bounds on the top are your covariance bounds. And basically what this is your model telling you, okay, I think that the error is going to be between these bounds. But you don't necessarily want it to be so far away from the bounds, otherwise you're over-constricting your model. So this is nicely in between, which is great. Then I have my control modes. As I mentioned earlier, there were 2 different types of control modes. So I had my detumbling and my sun pointing. For my detumbling, I decided to use a B-dot controller. Basically what this is it takes the derivative of your magnetic field and it tries to reduce it. So it gets rid of it. So it reduces also your angular rate. This is done by adding a negative gain. And this is a bit more of a slower controller. It takes a lot longer to stabilize. But for the case of this study, I had a 1,000-second simulator. As you can imagine, it's real time. So if I let it run for the whole period, it would probably, I've seen some things which say it can take up to 2 days. So if I was running a real-time simulator in 2 days, it's not very practical. So what I did was I tried to show that the decline in the angular velocity, in the angular velocity. The second mode was the PD control, was the sun pointing, which I used a PD controller, which is a very simple controller, and this is a lot more faster to react, as you can see here. So these are the results from the controllers. The first one is the angular velocity. As you can see, as time goes on, by the end of the simulation, the magnitude of this has gone down. And then on the other side, you can see my PD controller, and that one stabilizes in around 80 seconds, so really fast acting. Now lastly are my actuator models. This was very easy. I had my Magnetorquer in the grads library, and I also had a reaction wheel, so I was able to integrate those as well. Here I also introduced noise and error to make sure that it was as realistic as possible. The same process was done with the sensors, where I found actuators from different missions, I found the data sheets, and I used those values to predict my errors. Now this is my complete simulator, which actually answers my first sub-question, which is what components are required to develop a functional ADCS simulation and test environment, which we've gone over, which are all of these components. This is a bit more of a detailed view with the outputs. As you can see, many blocks, many connections. Just as reference, each one of these blocks I call blocks, and the lines are then the connections. Now we'll move on to, okay, how do we then make this a real-time simulator? And as we spoke about earlier, we'll be using Eurosim, so taking now that MATLAB model and putting it onto this new software, which is Eurosim. But before we go from that, I want to talk a bit about the hardware that I use to run this simulation. So the two different hardwares that I decided to use, or pieces of hardware components I decided to use, was the Raspberry Pi and the Orange Pi. I put the photo in there for aesthetic reasons. So the Raspberry Pi 5 is something that I'm sure everyone's played around with, maybe the Raspberry 4, 3, there's many generations of them. Very simple, you can get small low-end components, we've built a rover with it, they've built a spider with it, you could build basically anything with it. And an Orange Pi is a newer generation, a bit more powerful, and personally, my favorite. The reason for this is because so for student purposes, I can imagine you're walking around with your hardware, and the Raspberry Pi 5 itself has a micro HDMI cable, which is something that is very inconvenient, and I don't think it's something that people should be using. Personally, the Orange Pi has 3 HDMI ports, which I think are very useful, and you'll see why later on. So here's a bit of a cost breakdown as well. I looked at the 2 different configurations. I did run them both on the 2 pieces of hardware. Final tests I did do on the Orange Pi, as I say, based on convenience, but they were both capable of running these simulations. And this is a bit of a cost breakdown. I can imagine the budget of a student team being quite small, so I really wanted to consider cost factors for buying all these hardware as well. I did include a lot of maybe redundant factors. For example, your keyboard and your mouse, I can imagine you'll have them at home. But again, if you have a HDMI cable already, that reduces the cost of the Orange Pi already. But the Orange Pi is, as you can see, double the price of the Raspberry Pi. So there are some cost benefits. So now I've been talking about this software called Eurosim, but I just wanted to give a quick rundown of what exactly it is and how do you use it. Luckily, I was able to get the support of someone from Airbus. His name was Leon Bramer, who helped me use the software because it was something very foreign to me. Eurosim has 2 different types of interfaces. You can either have software interfaces, or you can have you can go through the back code. Personally, I went through the visual intuitive interface, but there were some limitations to it because there wasn't that much documentation. So through this process, I created a 12-step easy build process for people like myself. So as just a quick rundown, we have the model editor. Basically, all those blocks that you saw become a folder, and then all those connections become something in the parameter exchange. Those are the 2 things. Next was the schedule editor. This is where you tell the software, okay, I want this to start, and I want this to go. So in Simulink, you just let everything run, and it's automated. In Eurosim, you have to tell it when you want certain blocks to be activated. So this is done within the schedule editor. And so this is inside. You can see parameter exchange. Those are the different, me telling it, okay, now I want you to exchange between this block and this block. The last one was simulation control, and this is where everything is taken together. So you have your model editor file and your schedule editor, but there's a bunch of functionalities here which I think are very useful. So for example, you have the graphs. You're able to look through the different interfaces. You're able to add initial conditions, but you're also able to do something that answers one of my sub-questions, which is, can the proposed setup incorporate hardware in the loop? So here, one of the things you can do is you can record your data, but you can also add data. So this is a stimulus file. So basically what it is you can take file from a piece of hardware and take one of the blocks out of your simulation and put that data in instead. So you can run your simulation with external data. And this is technically not software in the loop because the data is not responding to the simulation, but it shows that you can start integrating different types of data. So in this case, you can add a piece of hardware and add it inside your simulation to create a hardware in the loop setup. Due to time restraints, I didn't do this part, but I was able to show that it is possible here. Now as I said before, there wasn't much documentation, and the help that I got was just from one person through email and a few one-to-one discussions. So there were a few things that I found were limiting. So what I did was start from a small model and then build it up. So you can see I started with 2 blocks, then I went to 7 blocks, and then I start integrating my final simulator. But through that, I found a lot of errors. So my main errors are listed here, but the main one I wanted to point out was the MUX function, which is the function on the top in Simulink. That one cannot be used when you port it to Eurosim. This is because the signals are not completely stuck to those inputs. When you compile this in C code, it basically switches them around. It says, okay, you have, let's say, 4, and it will just randomly plug them into the random port. So you'll get really messy data. But if you use a bus creator, which is specifically for signal generation, it sticks to those ports and it doesn't have the same issue. I had the same issue with randomization. You have to make sure that you always seed it, otherwise it just becomes chaotic. The same thing for repeating functions and copying blocks as well. I had that issue because I was using 6 sun sensors. So to automate this process a bit more, I actually created a compiler. So you're able to create these blocks a lot simpler. So with this code, you're able to set the parameters which are specific to Eurosim. This included making sure it was fixed time step. Of course, we were doing real-time simulation, so it has to be fixed time step, and I specifically chose an ODE 4. And finally, these are the results from my simulation. So the light colors are from Eurosim, and the dark colors are from MATLAB Simulink. As you can see, they don't completely align. The patterns you can see in the errors do match, but the lines don't overlap. So there was a lot of issue with this. I wondered why. In MATLAB, you have the execution. You can see the execution order. That matched the way I was doing Eurosim. But at this point, I had 17 blocks and over 107 connections, which meant that every single thing being manually done became more and more complicated, which highlighted the limits of maybe Eurosim at this point. It meant that checking those connections and where data was going became more and more complicated as the model got bigger, so this showed a limitation. So finally, my conclusions and recommendations. My last question that I didn't answer, sub-question that I didn't answer was, how can a real-time test bench be designed to meet the needs of student-led and institution-based CubeSats? Now, all the software that I used to create this simulator was education licensed, so I didn't have to pay for any of the software. I created automation steps to make the process of making that simulator easier. And I also managed to create the hardware setup in less than 400 euros, which I think is a reasonable budget for a team. So finally, through everything, I was able to get a sub 400 test bench that was able to provide software in the loop validation at 100 Hertz. I was able to show my BDOT and my PD controller, and my extended Kalman filter was able to provide robust state estimates. And finally, I did show that it was hardware in the loop was possible with this setup. This is, again, just a reflection on the main research question: to what extent can low-cost hardware and simulation tools support real-time testing of CubeSat ADCS algorithms in an educational context? And finally, my recommendations are for full hardware in the loop integration. So this can be I think it would be really cool to add some small hardware components. This can be a sun sensor or a magnetometer, but this is fully based on my own reference mission. And also to add some more automation steps. There is a time-consuming part where you have to decouple your MATLAB model and put each block into a file. And to generate those files, you can imagine, can take a long time. So if there was a way to automate that process, I think this whole process would get a lot easier, and you can iterate faster, and you would be able to find the bugs that maybe I found. And lastly is to maybe use more complicated control modes. I think it would be really interesting to see how time latency can be shown in real-time simulations as well. So that was everything for my presentation. Thank you so much for listening. If you have any questions, I'd love to answer them. Amazing.
So
Oh,
on your very early slides, you talked...
Do you have a number? Do you...
Probably not. But you were talking about the percentage of failures.
Yeah.
And you chose this, and it only represented 10%.
Yeah.
So obviously you could have chosen something that had a higher impact.
Yeah.
So...
Why?
Well, yeah, kind of.
Okay.
I'd have gone after the big percentage personally. But
Of course. So basically, in this case, the highest percentage was the electrical power systems and the communication systems, but these ones were mainly hardware issues. So when I looked into it, there were a lot of hardware issues, and that wasn't something that I was able to do within my thesis. So I chose to pick a subsystem that was majority software-based, so that I could use the resources that I did have around me. So also my supervisor was ADCS, so it was easier for me to build that simulator without having to struggle. Also electrical power systems, yeah, I would have to start incorporating really big pieces of hardware that slowly became more and more out of the bounds of what an education mission could accomplish. So that's why I chose to use ADCS. I hope that answers your question. Yeah.
Yeah, I mean, first off, thank you very much. This amazing job at breaking it down. Like, you cover so much complexity, and I was able to follow it all.
Oh,
so that's
thank you.
Really great. I was wondering just, why is it important that we must use Eurosim, for example, validated software, instead of just me starting from scratch? So.
Yeah, so Eurosim I chose because it was used in other missions as well. That didn't fail, so that was the first indication that I thought was a good sign. Sorry, could you repeat your question? Why was it important?
Why is it important
that I use Eurosim?
This existing software?
Yeah, so if you had to create, so even when I was using the grads library, that was the reason I did that was to make it a bit more of an easier process to build something. I feel like if you really wanted to build a really in-depth simulator, it becomes quite specific, and then you can't use it for general cases. So I wanted to create something that everyone would be able to get access to, and then could build upon themselves, rather than, okay, this is too built for this purpose, so I can't use it. So I tried to make it as general as possible, basically.
Nice, thank you.
All right.
Eurosim development took 10 years.
Also that.
Hard real time is, for us amateurs, it's impossible to do.
You can try. Yeah. Yes.
I had a question about one slide where you have a graph about the gyroscope and like the errors that you have added on it.
Yeah.
Can you explain a bit more what type of errors you implemented and what they mean?
So here I introduced, within my thesis I did have all the values written down. I don't know them off by heart, but from looking at it, there is a little bit that, well, there's noise, first of all, because it's very chaotic, but there's also a little bit of a deviation. From here you can see it's slightly above the 0, but this one it's going towards the 0, so I think it's slightly deviated as well. There was also some delay, so when you gave it a command, it took a little bit of delay before it actually moved as well. So time delay, things like this.
You implemented all of these errors at the same time, not one by one?
When I implemented them, they were done one by one,
Right.
to check that they were doing what they were supposed to do. This is all of them put on together.
Right.
Some of them are larger than others as well, more major factors, things like this.
Thank you.
Yes.
First of all, great presentation, by the way, I think it was amazing. I have a bit of a question of curiosity or interest, because this is obviously a really well-intentional project for student teams and could be used for educational purposes, which I think is great. I just wanted to, out of curiosity, ask if you've already, put into plan any sort of collaboration works, or would you like to work with a
Yeah,
student team?
so actually Eurosim itself is a bit harder. So when I started the thesis, it was something that was continuously being developed, but since starting it, it's actually come more to an end. So you can still use the software, but it's less accessible. But I did start talking to, there's a CubeSat team within Aerospace that wanted to look at maybe implementing this sort of testing method. And as it's a bit more broad, I think it would be very useful for them to use as well. So that's something that I'm looking into, yeah.
Super exciting.
Thanks. Yes.
I have a small question which perhaps is not super relevant to the subject, but you showed us at one point the graph which had the exaggerated sun movements, and
Yes.
I got a little bit lost as to the relevance of why you did that, but you specifically made the comment about that being actually detrimental if it happened in real life.
Oh, right. So this was more of a unit test. It was more to see if the sun sensors were being activated when the sun vector was in their field of view. So each one of these circles was the field of view of that sun sensor. And there's areas where the sun sensor is not activated. So I wanted to test that these movements were actually being recorded. So I created more of a visual way of inspecting that movement. Yeah. So it wouldn't. This is not what I want it to do. This is more of an exaggeration just to make sure I'm checking that it's activated when it's supposed to. Yeah. Nice question. Thanks. Yes.
They're analog sensors or are they digital?
They're analog sensors. Any other questions? Yes, Serena.
I have another question for you. Regarding the controllers, you chose VDOT and PD controller.
Yes.
What was the main reason you went for these two and not, for example, for PID?
Yes, so I tried to really choose the simplest controllers or controllers which were already being used for these specific purposes. The BDOT controller was passive, so there's no moving parts, which I think is, it is used in CubeSats which have a lower resource yield, or resource mound, let's say. So that's why I chose the BDOT controller. The PD controller is just a simple controller, and it was appropriate for this pointing, so I used it here. Thank you. Any other questions? That was a lot of questions. Do you have a question? Oh, okay. Yeah.
What
They don't have
what
any.
would be the first step that you would do if you could continue this work? What would be your first step to improve, to add to the whole work?
So what I would want to do is create a sensor that I could then plug into Eurosim. So as I talked about, there was hardware in the loop possibilities. I only managed to test using a stimulus file, but I would like to actually integrate some sort of live sensor into it. Even if it fails, it would be great to see that movement of data. So I think that would be my next step.
But just for the information, it has been used for many of the actual satellite projects. So they use Eurosim as a baseline software for all the hardware test benches for actual satellite designs and missions. So it has all the interfaces for all the hardware that we want to test.
Thanks. Thank you.
Okay, so if there's no more questions, thank you once more. Well done. As I said, we will be going to another room now. In total, it will be taking about 1.5 hours. So if you are still around here, please come back after 1.5 hours, which is 11:30 or 11:40 or something like that. That concludes it for now. Thank you for being here.
Thank you.
And hope to see you later.
Thank you. There's also snacks here as well, and I created a little quiz for you guys to do while I'm away. Thank you. Wow, printed. Okay, I follow you then. Should I leave this here?